Hello. Welcome you all to Ultrafast Light Sources for Quantum Application and Accessories webinar organized by Laser Science Services. It is with great pleasure that I introduce our speaker for today's webinar, Matthias, with a strong academic background and a wealth of experience in the field of ultra-fast physics and photonics. Matthias brings a unique perspective and expertise to our discussion today. So I will now hand over this webinar to Mr. Matthias.
Hello. Yeah, thank you for the introduction. Just figure out yet Zoom related stuff. Yeah, thank you for the introduction. Today I will talk about ultrafast light sources and how they can be used for quantum applications, especially driving quantum dot structures for single photon generation. Sorry, I have to, yeah. So here's the outline of my talk. I will introduce very shortly APE, the company. So I'm from APE. Afterwards, I will focus on the main part, this ultrafast light sources for quantum application. And there are essentially three subparts. One is complete light sources that can be used. Then also what can be done to improve already existing light sources in your lab to make them feasible to be used for this quantum applications, and showing various examples where what people have done with this kind of quantum systems. And finally, I will talk a little bit around about accessories, devices for quantum applications, especially here, accessories for ultrafast laser sources, and how they can be diagnosed and modified to be best suitable for quantum dot excitation, which then can be used for quantum applications. Yeah, so let's start with a short introduction of the company. In principle, APE stands in German Angewandte Physik und Elektronik GmbH. In English, it's like Applied Physics and Electronics company. And APE manufactures devices for generation, characterization, and modification of ultra-short laser pulses. And the devices are used worldwide in industry and research. The company has now already 31 years, so was founded in 1992 and is located in Germany, in Berlin. There we have the headquarters, the production. The company has now like 65 employees, 13 R&D labs, 3 clean rooms, and let's say the 30–40% of the employees are actually in the R&D department. So we have very strong focus on developing new customized solutions for the customers, and to really try to adapt to new changes in the industry. And therefore we have also this ultrafast laser sources for quantum applications, which is a rather new field or as a new attention over the last year got this application field. All the devices are designed, manufactured, and assembled in Berlin, and our prime products are essentially autocorrelators, where we'll talk a little bit more afterwards, and ultrafast OPOs, which stands for Optical Parametric Oscillators, which are ultrafast light sources with tunable wavelength. On the bottom you see a little bit some numbers from the company. Kind of interesting, essentially here at the end, on the right side, we see 2018, essentially, we saw the first excitation source for quantum applications, and from there it really expanded quite this applications for us. The general product portfolio from APE covers a wide range, so there's essentially 3 main branches. One is we produce tunable ultrafast light sources. So ultrafast really means your femto and picosecond range, so no nanosecond, no other ranges. And our light sources are based on optical parametric oscillators and harmonic generation. So we can really cover the full range from UV to mid-IR. And furthermore, we also, the second branch is diagnostic tools. So diagnostic devices for ultrafast lasers to measuring what is really coming out. And the third branch is pulse manipulation. So this means you have already your ultrafast laser or light source that you buy from some company, and then afterwards you want to change the properties of these lasers, like the spectrum that comes out, the pulse repetition rate that comes out, want to modulate the pulse chain. And this can be all done with our devices. So the nice thing is about the full combination that it gives us the full capability to create really customized and user-oriented solutions. Yeah, so let's dive in the actual topic. Ultrafast light sources for quantum applications, and starting with the full package, essentially a complete source. A little bit motivation. I guess most of you know the quantum science application has become a very large field of investments and fundings over the last years. So just some examples are this Indian National Quantum Mission, or for example in Europe it's the Quantum Flagship funding initiative. But there are many others all over the world, in US, in China, in many other places. So it really is a very interesting or a very a field where a lot of large investment and funding got available over the last years. The main reason is that these quantum technologies, or harvesting the quantum probabilities, have huge potentials in comparison to actually devices which are more based on classical physics, especially in fields like quantum computer, quantum simulation, also quantum communication, quantum security, quantum cryptography, but also for other fields like imaging, metrology, and so on. And it's actually quite a wide field. There are many technologies, many different directions in this quantum, this area of, let's say, quantum technologies and quantum applications. And actually, we are focused on a specific part, which is that for some applications like quantum communication, quantum encryption, or quantum imaging, one need actually a new type of light sources compared to the classical light source, which are single photon sources. And single photon sources in the sense that these single photons then have quantum physics properties, like that you can create, for example, entangled photons, that the creation of the single photons are deterministic, that they are indistinguishable, and many others. So there are essentially new light sources needed for especially quantum communication, quantum encryption, and imaging. And one promising approach to do this is actually optical pumped semiconductor quantum dots. So this means you use some quantum dot structure, here shown on the left, for example. This is just an example, but there are many types and structures, different materials, growing methods that people have shown, but use some kind of quantum dot structure. You excite it with a pulse laser, an ultrafast laser, and then under certain condition, if you do it right, you can get your single photon emitter with, in the best case, good properties for quantum applications. And what we do in this chain is essentially we design and provide, fabricate specific light sources for to excite, to pump the quantum dot structures. Maybe just a quick reminder: quantum dots is a very small nanostructure in the range 1 to 100 nanometer size. I would say there are a lot of different approaches how to grow them, which kind of material to use, which kind of sizes, structures one can use. And it is important to know in this context that the different kinds of quantum dot systems have varying excitation wavelength and also bandwidth. So this means you, if you want to study a variety of different growing methods for quantum dots or different quantum dot regimes, then you need a very special light source that can address all these requirements. So yeah, here maybe just a short brainstorming, essentially, what would be an ideal pump source, excitation source for quantum dot single photon emission. If you use, for example, compact diode lasers, then you have a narrow bandwidth, which is good for the excitation of quantum dots, and you have a high repetition rate, which is also great, but you have the problem, you have a fixed center wavelength. So features or other properties that compact diode lasers can't give you, for example, would like to have tunable wavelengths, because, how I said, even in the same sample, depending how you grow the quantum dots, different quantum dots can have slight variations of the excitation wavelengths. So if you use a diode laser, it can be that some quantum dots you can excite, others you can't excite. Then, for example, if you change material, if you change, if you want to go to different wavelength ranges, to use, for example, transmission windows of optical fibers, then yeah, it would be greatly beneficial if you have a tunable center wavelengths. Furthermore, it would be nice to have a tunable bandwidth, which then comes also with a tunable pulse duration, because actually, if you achieve that your excitation source has a similar spectral bandwidth as the absorption spectrum of your of the transition that you want to excite from the quantum dot, then you can have this coupling energy most efficient. And this actually, yeah, it would be nice to have this what you want. Furthermore, high peak powers would be nice, because then you can use multi-photon, or especially two-photon excitation. This will be shown in some examples of user experiments, where this actually has great benefits to use multi-photon excitation in a quantum dot. And obviously, if the whole source is fully optimized and stable, it would be also highly required. So all these requirements essentially can be covered by light sources that we offer, for example, and this has advantage, especially compared to diode lasers, for example, or fiber lasers, that it's very versatile, a flexible device, and it's perfectly suited for area where the required parameters of your light source are not exactly known, or you want to play around, or you want to go maybe in the future to a different spectral range that you want to investigate with your quantum dots. Really essentially for industrial R&D and the scientific community. Yeah, here's our approach in a nutshell. So essentially we combine via frequency conversion an optical primary oscillator, where the pump lasers include, so it's a tunable, all-included turnkey light source. Pulse duration of 2 picoseconds. The tuning range of the wavelengths from 700 to 1950 nanometer with some gap. And the source is fully auto-created, automized, and essentially turnkey hands-off operation. Really like a normal laser, no? A normal system that you can buy. And then we combine this with what we call as a spectral slicer, which is a 4F shaper, so essentially a 4F imaging system, where in the Fourier plane is adjustable slit. So you reduce on purpose your spectral bandwidth of the laser. This system is fully optimized, and you can achieve essentially extremely narrow bandwidth down to 50 micro electron volt. Yeah, if you then essentially calculate the result rather than pulse duration due to the relation between the bandwidth of a pulse and the pulse duration, you can get up to 50 picoseconds. But the nice thing is essentially, since it's adjustable slit size, you can vary the bandwidth. So you can essentially, you don't have to use the smallest bandwidth, but you can have the full laser bandwidth and all different bandwidths in the middle. So you can really adjust to the bandwidth or excitation resolution that you need to excite your specific quantum dot structures. So, and then the key features here again shown essentially, here's the system on an optical table. So it's a rather big system, but has the big advantage that you can cover wide wavelength range. Then there inside are a lot of optical fiber telecom bands, like the OESCL band, which is actually quite interesting because a lot of research is done for quantum dots in this kind of bands, especially I think the C band. Because if one can create their good single photon emission sources with good quantum properties, then it's easy to expand this kind of system for the existing optical fiber infrastructures. Then our system has a high peak power, can drive 2 photon emission processes, and I said adjustable bandwidth, and therefore also adjustable pulse duration. And it's all automated stable operation, and yeah, can be tuned easily. This is essentially the complete light source. So now let's talk, which may be also quite interesting, what happens if you have already a laser in the lab, which is maybe not as good suited to excite quantum dot structures, but you would, can you do something? Can you put some device behind it to make it accessible for quantum dot excitation? And without having the need to buy a new laser. And there we offer different possibilities. The first is that one can place this pulse slicer, the spectrum slicer that I showed before, behind your device. So we have many customers that do this actually, who have femtosecond, picosecond sources like sapphire layer sources. Just to name some names, for example, like a Chameleon Ultra or a Discovery or Insight or whatever, like a kind of femtopicosecond laser. You can combine it with a pulse slicer afterwards. And the big advantage is that you cut your spectrum. Here on the right top side, you see an example where the blue line, essentially the spectrum of the light source of the sapphire laser. And then after the pulse slicer, you get this very nice shaped, Gaussian-like spectrum afterwards. And you see and then this spectral width can be tuned, optimized, and calibrated. So you just have a software, put the numbers in that you want, and the center wavelength shift is the bandwidth shift. It's very user-friendly. And this makes essentially possible that you can use femtosecond lasers also for quantum dot application, because the problem is normally intrinsically there's not very like if you only have a femtosecond laser, it's hard to use it for this kind of quantum applications because the spectrum is too broad. There is a high risk that you excite transitions in your quantum dot or in your structure that you want to excite. So you can have a background noise, background transition that you don't want. Then essentially the idea of all the single photon generation doesn't really work so well. And it's very hard to get really quantum properties of your single photon source. The second way to extend your already existing laser is you can use optical parameter oscillators or harmonic generators to extend your wavelengths. So for example, you have an existing laser at 550 nanometer or at 800 nanometer, sapphire lasers, or terbium lasers at 1030 nanometer in femto or picosecond. And then you can extend it with optical parameter oscillators or harmonics over a wide spectral range. So here on the bottom right side, you see this graph where essentially shown like in dark blue, you see the accessible wavelength when you have a 515 nanometer pump, and in the center in light blue if you have sapphire pump, and then in yellow if you have 1030 pump. So for example, if you go to the middle line, the blue line, you see there that around 700 to 1,000, 50,000, 80 nanometer, you can have your emission of your sapphire laser. But by using an optical parameter oscillator, you're now also able, with a signal beam, for example, to access the IR. So to access 1,000 nanometer up to 2,000 nanometer. And further, if you go to ITLA, DFG. So this means instantly you extend your usable range from the visible, the NI range with the sapphire to the IR, which is especially interesting for quantum dot research, since I said before in the IR, like around 1550 nanometer and so on, there are a lot of interesting telecom bands, which are interesting for quantum dot research. And of course, all these systems are essentially fully automated, flexible, can be interconnected with the software. So there is a huge flexibility here. And on top, this can also be combined with the slicer that I showed before. So you can, even if you have a femtosecond system and then access to further wavelength ranges, you can combine it with a pulse slicer, spectral slicer to further reduce the wavelengths to address exactly the wavelengths of your quantum dot, or your the bandwidth, or the excitation of your quantum dot that you want. There are a lot of possibilities. And then the last option to extend your existing system are essentially multi-box solutions. This means since we have all these devices, it's very easy for us to also adjust for all kind of custom questions. So you want multiple output wavelengths, bandwidth. You want varying repetition rates with the different output beams. You want other wavelengths if possible. You want higher repetition rates than actually, and all this kind of things. So there are a lot of possibilities. Here, for example, just showing one possibility on the right side. This is a system from a customer from us, which has essentially one driving source, a chameleon ultra, 2, and this source then drives on the to the bottom an OPOX and let's say frequency converter, optical parametric oscillator, and then on the top you can either choose to go for an other OPO, or you can go to second harmonic. And then after the second harmonic, you have a pulse slicer, and also after the below OPO, we have another pulse slicer. This means you can, with this kind of system, you can now create at the same time a very narrow spectrum with the OPO, for example, the signal range. So from, let's say, around 1550 nanometer. And at the same time, on the top with the harmonics and the pulse slicer, you can generate very small pulse around 400 nanometer, or if you don't use the harmonic, you can have small pulse at 780 nanometer to do some kind of pump probe or some kind of multi-photon excitation schemes. So there are a lot of possibilities here for very customized requirements. So to maybe shortly summarize this part, they're essentially in order to excite quantum dot structures for single photon excitation or single photon generation, you can use complete sources where you get essentially the laser, all that kind of thing together, all optimized. You can use also, if you have already a laser in your lab, because the laser is actually typically the most expensive part of this whole systems, you can get a spectral slicer behind to make, for example, Ti-sapphire broadband, Ti-sapphire lasers feasible for quantum dot experiments. You can also use wavelength extension to go to different spectral ranges, which are before not possible with your existing laser. Or you can do all kind of customized systems depending on your actual specific needs for your experiments. And now I want to show some examples, some publications from customers which use essentially these kind of systems in the laboratory and excited quantum dot structures for quantum applications. The first example here is from Schweikart et al. This is the group from Professor V. Swiller in KTH in Stockholm, in Sweden. And they showed essentially that by using a 2-photon resonant excitation scheme of bi-exciton transition, that they could show one on-demand generation of background-free single photons from a solid-state source. So this means due to this 2-photon resonant excitation, they could actually show extremely small second-order coherence. And here on the right side is essentially the references there. Then the same group also showed that this experiment was done at, I think, 780 nanometers, something around this, the Ti-sapphire range. And then they went here to the telecom C-band. So essentially, they showed single photon and cascaded photon pair generation in a telecom C-band. And in their particular publication here, they showed that they can tune the photon energy to very high precision using piezoelectric structures. So they are playing quite a lot with different quantum dot structures or quantum dot growing techniques. And I have to say, like this example and the sample before, this is all the same light source that they have. So they have essentially an OPO, a Pico Emerald system, and then they have two pulse slices, the one for the visible output and one for the IR output. And so they could essentially perform the two experiments over the years with the same devices. And then essentially they combined these two ideas from before and showed essentially on-demand generation of entangled photon pairs in the electron C-band using this phonon-assisted two-photon excitation scheme. And yeah, and in the center here in the sketch from their publication, you actually see on the left top in this quarter there, like the excitation source, which is the laser, that's a black box. And then there is shown the pulse slicer or the schematic of the pulse slicer. And then how they excite and detect the single photons. Yeah, and some other applications here, for example, a group from Caspar Hoffmann et al. From Institute of Integrated Nanophotonics in Dresden in Germany. They used the long pulse picosecond optical parametric oscillator source in the study here, heralded preparation of spin qubits in droplet-edged gallium arsenide quantum dots using quasi-resonant excitation. And they could show the first comprehensive study on deterministic spin preparation employing excited state resonance of droplet-edged gallium quantum dots. Maybe last example, Christopher L. Morris et al. From the Harry and Watt University, Edinburgh, UK, used existing already, so they had a Tie-Sapphire laser in their lab and they used combined it with a pulse slicer to use the bandwidth. And then they could probe the role of coherence in cooperative emission arising from view distance, but in solid state emitters from this publication shown here. Sorry. So this shows you there is, I mean, probably aware that there are a lot of research going on in this kind of field. So how one can engineer the quantum dot structure properly, or how you can excite it properly to achieve very desirable quantum characteristics of the single photon or single photon pairs which are emitted. There are a lot of research going on, and this kind of advanced coherent light sources can really leverage to achieve novel new results. Yeah, and in the last part of my talk, I would like to talk, how I said before, about some accessory devices which can be used for to characterize, to manipulate ultrafast light sources, which are then used to excite the quantum dot structures. Yeah, so one thing is a spectrometer, a wave scan. This is meant to be a spectrometer to measure the spectrum of your light source, so of your laser. So it's not a single photon detector or something. It's really like typical laser spectrometer. The nice thing about this device is that it's at very high resolution and broad bandwidth coverage. So on the bottom left side, you can see essentially different versions and the wavelengths. They're just missing nanometers. Essentially, all the numbers which are given there are given in nanometers. And you can actually see, you can cover a very wide range. And the actual nice thing about the spectrometer is that typically, if you have spectrometers which go above 1 micron, they become very fast, quite expensive due to the detectors which are used there. And in our design, because we use a specific Chesney-Turner design with a rotating grating, we are actually quite cost effective because we don't use detector lines, but we rather use just one single detector to measure the spectrum. And still, you're measuring very fast with a 5 Hertz scanning rate, so in 5 Hertz with your spectrum, 5 spectrum per second. So this is very, very fast. Yes, and in principle, the idea is obviously if you go from to ultrafast light source with tunable spectrum, you actually want to be sure that the spectrum that is coming out actually is the spectrum that you want, because If you have a fixed frequency laser, then you know what you have, but especially with tunable systems and they're cascaded, it's every time good to be able to actually verify for your experiments if you really get the wavelengths, the center wavelengths that you want. Another accessory is our autocorrelators. So for the people who don't know autocorrelators, essentially these are devices which can be used to measure the pulse duration of ultra-short pulse. And obviously, normally, if you buy an ultra-fast laser, then you get a data sheet and there's written some number, and this number is true. You could also like a test report, know what they measure when they install it and when they fabricate the laser. But what happens that typically, one thing is there are some lasers where you can actually tune the pulse duration. Okay, so it would be nice to actually know what is the actual pulse duration. And the other thing is that even if you have, say, Sapphire amplifier or something like this, anytime if there's some kind of compressor involved in this scheme, it can be that over time there's some degradation of alignment, so that it can be that the actual pulse duration changes over time, so it gets longer, slightly longer, but you don't see it necessarily on the average power, which is a parameter which is very easy to measure from the ultrafast laser. And then in terms of to validate your experimental conditions, especially when the peak power is very important for experiments, it's very, from my perspective, important to know essentially what you're actually using to drive your experiments. And we have also, so typically autocorrelators need a collimated beam, but there are also types of autocorrelators which can, like in our case, it's called CAPE, which can measure the pulse duration of a focus beam. So under a microscope, after focusing lens, depending on your setup. So this can be also very useful. And the device is very easy to use, plug and play. You can use fiber input, free space input. You can program to programmable APIs. You can remote control. There are a lot of, let's say, nice features, but in principle, the basic idea is to measure the pulse duration of an ultrafast source can be very useful or even important to validate your experimental conditions that you're using for your experiments. The nice thing about our autocorrelator is that it's very modular, so you can actually, the customer by himself can easily, with magnetic mounts and so on, change crystals and detectors. What I mean by this, that by using this possibility, we can actually cover a very huge range of different wavelength, of different pulse duration, which you can measure, and also of different input powers. As you see, essentially some overview, just to give you a perspective, ignore the details. In principle, the idea is really the customer by himself can easily change or use a wide range where you can characterize laser source, pulse duration of laser sources. And what is also crucial to know, they are upgradable. So this means, for example, if now you have a Sapphire laser in your lab, you buy a certain autocorrelator with an optic set and you measure your Sapphire laser. But then in some future, maybe your colleague in the other lab gets another laser in a different wavelengths, or you want to put an optical parametric oscillator behind, or harmonic generation. You don't have to buy a total new device. You only buy the respective optic set that you need, and you extend essentially the capabilities of your autocorrelator. So it's a very, let's say, it can be used for many, many different sources that you have, and it's very versatile device, which makes it, especially if you want to use it for many different lasers, a quite, let's say, cost-effective method or approach to use this modular design of the autocorrelator. Furthermore, this is maybe more interesting for people who really, really have short pulses. So broadband lasers, for example, Sapphire lasers or turbine lasers with pulse durations below 100 femtoseconds. That would be also nice if the pulse really gets so short to actually don't just measure an autocorrelator, where you get an kind of an estimate of the pulse duration, assuming a Gauss shape or sec-square pulse shape, but you can actually measure the phase and the amplitude of the pulse in time. So you can actually, get even more information. And the nice thing is here that this frog is also not a separate device in our case. It's really part of the autocorrelator. So you can upgrade easily the autocorrelator with a certain optic set. Here on the top side is shown like there are different crystals. You put them in, change some mirror, and you automatically change your autocorrelator measurement device to a frog measurement device. So this is a very, very versatile combination. Maybe to mention one more, essentially the spider. This is also a technique to measure for short pulses, phase, and amplitude, where you can characterize a complete pulse characterization. And the difference to our scanning frog is essentially the spider is single shot capabilities, and in real time you can calculate the pulse at the phase of your pulse. There are different versions for the few cycle short pulse versions, and so this means especially for amplified high sapphire lasers or for amplified very short cherubim lasers, you can use this kind of devices to seal online shot by shot, even if the repetition rate, let's say 1 kilohertz, what is the actual pulse duration, how it changes, for example, if you change anything of the laser settings or on the compression. And especially for these very short pulses, typically you can't rely on the specifications which are given in a datasheet when you buy the system, but you actually have to measure them, because if the pulses are really short, like let's say in a range of 50 femtosecond and so on, they change over time, because just the thermal effects and so on, the alignment a little bit changes of system, so they have to be essentially fine tweaked quite often. And the system comes with an elaborated software where you have a lot of representation of electric field, which is calculated. It's easy to align the setup, so there are camera-aided motorized mirrors inside to easily align the device, and you can have a lot of theoretical additional values about your information about your pulse. Yeah, maybe the last device I want to highlight is pulse picker. In our case, we call the device pulseCheck. And the idea is here that you have your ultrafast laser source with a certain repetition rate. Normally, like high sapphire lasers run 80 megahertz or 78 megahertz. And now you have the problem maybe that you want to run an experiment where the detection system of the experiment or is too slow, or that, for example, the dynamics that you want to see are too slow. The problem is that you excite with 80 megahertz, that you can't essentially brewing between the pulses, and you can't distinguish each event individually. This is actually quite important for this single photon sources, because what you want to do there is actually you want to, for each laser shot that you do, you want to create one single photon in the best case, or a single photon pair. And then you want to analyze it with some single photon detection, with some setup in between. You want to use this single photon for some experiment. And in case that your detection system is too slow, or there are like other delays, dead times of electronics, this can be really a problem. So with a pulse picker, you can actually actively reduce the repetition rate of your ultrafast laser and adapt it quite like freely to the repetition rate that you want. So in principle, there are different versions, but in principle, for example, we can cover there all the wavelengths from 340 to 1600 nanometers. And this kind of device is compatible or combinable with all the different systems or the approaches that we showed before. So there's no problem with to combine this if it's necessary for your specific needs. Yeah, thank you. With this, I would also, I'm at the end of my talk. To conclude, ultrafast light sources are a very perfect tool for quantum dot excitation, and in this context, especially then for to use this quantum dot excitation for single photon sources, single photon generation, and using this then for quantum technology, quantum research. To do this, one can do it with simple fixed frequency lasers, but especially if you need flexibility and versatility in your research, what you do, you would like to have advanced light sources. And AP offers a lot of this kind of light sources, for example, providing tunable bandwidth, providing tunable wavelength. The systems are fully automized. You get spectrally narrowband pulses. And on top of it, we also offer a lot of add-ons, improvements of your assistant lasers like bandwidth reduction, flexible pulse repetition rate, or others. And there are also a variety of diagnostic devices for the ultrafast light sources, which are especially interesting in case when their wavelength and bandwidth, and therefore pulse duration, is tunable. So all in all, this advanced light sources can give you huge versatility and flexibility for research. Yeah, thank you for your attention.
So hello, Matthias. This is Jagdish here.
Nice
thank you very much. That was a very wonderful talk. You gave a very clear explanation of all those things. I basically have two questions, Matthias. So initially, when you said people are using the Sapphire lasers, and then you also said using a 15 nanometers as a pump, you can do the lasers, and also you spoke about the pico emerald. So when I consider the pulse duration, one is a 2 picosecond, the other one is like a 140 femtoseconds, and the third one is as a different femtoseconds. My question is basically, how critical is the pulse width as a pump source for the quantum light source? Is it a picosecond will be better or a femtosecond will be better? And will a bandwidth play an important role? Because bandwidth of a cheminion lasers are like 10 nanometers to 15 nanometers, whereas the other lasers has a different bandwidth. And my second question is, will a repetition rate of the laser also matter in the selection of the light source? These are my two questions. I will look forward to your reply. Thanks.
Yeah, thank you. Thank you very much. First of all, essentially pulse duration and the bandwidth. So in principle, what I understood, essentially talking to the people that use light, or that were interested in this spectral reduction, that typically pulse durations that you want are in the range of 10 picoseconds, and then the respective bandwidth. So it depends then on the center wavelengths when it's to calculate, but in principle, and also like in this kind of field, they typically talk in terms of, if I understand right, in bandwidth, not in nanometers, but either in energy space, like in electron volt or micron electron volt. Or sometimes it will be confused with all the different numbers. But what I understood, so the desired range that you want to have, or what is the bandwidth of the excitations, typical excitations, what you want to drive, are in the range, let's say, 10 picoseconds-ish. If you use a laser which is much shorter, so which has a much broader bandwidth, like for example, Sapphire oscillator, femtosecond Sapphire oscillator, then you have the issue that first of all, a lot of energy is lost anyway, because you can't, like, just the overlap essentially will be absorbed from this transition. So there's a lot of energy which doesn't couple to the quantum dots. And the second thing is that you can actually excite a lot of other transitions, maybe transitions in your structure, and this can lead to background. So essentially, what you normally do, like the aim is essentially how I understood it, that you have a pulse, which a lot of photons, which comes to your quantum dot structure. In the best case, you have essentially one quantum dot there, which you, depending how you couple it in, excite. And then in the best case, you would have to have essentially one single photon out, or one single photon pair, which is maybe entangled. And so the problem is we now have a lot of other wavelengths which are maybe exciting other transitions, or which are exciting the bandgap of the material, raw material below, or some other things. Then you get automatically background photons, and this essentially diminishes, or depending how you use it, can give you a big problem. so I'm not exactly an expert in this field, but this is what I got, that is actually quite, especially when we use femtosecond sources, there is a huge concern that you have a lot of, let's say, background noise, background photons, which are not created by this quantum dot and therefore don't have any quantum properties. And then, or not the desired quantum properties if you want. And then, of course, it's a question, okay, if 10, let's say 10 picosecond is perfect, I guess this varies also with the specific quantum dot that you want to address. But if, let's say, 10 picoseconds are perfect, can you also use 2 picoseconds? Can you also use 50 picoseconds? I guess for excitation purposes, there's no problem, you can do this. But how I understood, actually, it's this very, in a perfect world, if you can tune the bandwidth, it's actually very desirable to have it kind of matched or very close to the excitation bandwidth, what you need, or for the bandwidth of your transition, because then this coupling is most efficient. And what you actually want as best possible coupling or efficiency, because you want this ratio, let's say in the best case, you want to create for each pulse that comes with a lot of photons, excitation pulse, you want to create in the best way one single photon or one single photon pair. Obviously, this ratio is not exactly 1, and people try to get this 1, but essentially this is the aim. So the best coupling and then least background noise that you can have is essentially desirable. Yeah, and then the second question was about the repetition rate, I think. Yeah, it's a good question. So I'm not, so essentially many people, many customers that we have, they use sources with, let's say, 80 megahertz or even higher. Some have systems with 60 megahertz, with 160 megahertz or 320 megahertz, then using an OPO and then using the pulse slicer to reduce the bandwidth. So I guess for their approach, there is no need to reduce the pulse repetition rate, because the detection scheme that they're using has no limitations there, or the limitations are not given there or not reached there. But we know from other applications, I would say I'm not so familiar with all the different fields or all the newest research which is done in this quantum field, because it's quite rich and there's a lot of going on in a very rapid pace. But I guess if you have, let's say, elaborate detection schemes where the detection scheme just can work at 40 megahertz, 40 megahertz or 20 or whatever, 1 megahertz, then it's highly desirable to reduce your pulse repetition rate, because you actually want to match with your source what is possible with your detection source. Yeah.
Thank you very much, Matthias. I think it's very clear. And in this aspect, I also feel the Pico Emerald is much advantageous because of the points you explained. Thank you very much, Matthias.
Yeah.
So, next question, please, if anybody wants to ask anything.
I think I see there are some in the webinar chat. There are some questions.
Yeah,
let's
see them.
Yeah, there's one question from Matthew. Do you sell single photon detectors? Which laser source is optimum for terahertz condition? Yeah, so unfortunately, I mean, we don't sell single photon detectors. There are different companies on the market. I said there are also like a lot of going on, and the field is growing fast. Yeah, we don't sell single photon detectors because it's not really our field of expertise. And yeah, there are many companies who drive it really to the extreme, like to improve the efficiency, detection efficiency. And then I think there's also a big merge in all this when one's setting is found where single photon source and a single photon detector match that, then to go to devices or to scale this, then people also want to reduce size and cost and all this kind of things. So yeah, but yeah, we don't sell single photon detectors. And then which laser source is optimum for terahertz conditions? I guess I'm not exactly sure what exactly essentially this question is referring to. Is this question more like really terahertz generation with terahertz emitters, or maybe the Matthew can comment? I mean, in general, there's a little bit different field. So if I understand the question right, I guess so. There's in terahertz spectroscopy, there is I mean, this is a field which is like, I don't know, 30 years old. I mean, there are a lot of research over the last decades, and people use essentially ultra-fast lasers to excite terahertz emitters. There are different also techniques and structures which are used there. And I think, yeah, the different approaches. So there are many people who use, for example, Thai-Sapphire oscillators and so on. Other people use amplifiers systems, so less repetition rate, higher energy. And I think the question here really comes down to what you want to use the terahertz waves for. So if you want, yeah, a high flux, or if you really want high peak powers of your terahertz beams, and what you want to drive with it. Especially if you want to drive some nonlinear process with terahertz beams, it's probably preferable to go to kilohertz systems, and but really not an expert in the field. So I guess there it's really good to dive maybe a little bit in the literature and see what people have done there and what kind of things are out there or published there. But I think it's mainly driven by what kind of experiments you want to do with your terahertz radiation. Here's another question. A single autocorrelator, can I use two different detector mode, for example, photodiode and PMT? Okay, so for a single autocorrelator, so if you buy one autocorrelator device and you have different optic sets, let's see, I just repeat a little bit, essentially this graph here now. So you have essentially one basic unit of the autocorrelator, and you have a lot of different optic sets that you can buy, that you can use. So let's say the difference between in each raw, you say essentially the different wavelengths, and the difference between on the top photodetector, photodiode, in the middle photomultiplier, on the bottom 2-photon absorption. I mean, especially the difference between the first and the second is so between the photodiode and the photomultiplier is sensitivity. So if you have a photodiode, it's like the standard thing. If you have a good pulse energy that you can use, and then if you have a very weak signal, like for example in fiber lasers, when you develop fiber lasers with very low energy or so on, then you would actually more use a photomultiplier. And yes, you can freely use your one base unit and there's two optic sets, and you can freely use between a photodiode detector and a photomultiplier. So in fact, each different color in the scheme means that every time you change the nonlinear crystal, which is inside, because it's a second order autocorrelator, you have to change the crystal, and you also change the detector. So this means you really change between a multi-photoplier detector and a photodiode detector. And this is very easy. So the customer itself can do it. This is all, there's no realignment and so on. You just align the thing once, and then you can change the detectors and so on. So there's no, yeah, there's no something very, very easy to do what our customers do on a daily basis, or on a daily basis. But it's possible to do it on a daily basis if possible, if needed. Yeah, then there's a question again from Matthew. Could you please share the basic version price of femtolaser? Yeah, I guess this is a question then this is in webinar chat for laser science. Yeah, I'm also not sure if with femtolaser, I think there's a company which called femtolaser. If you mean like laser from femtolaser, I guess I don't know actually if laser science is the representative for femtolaser in in India, or if you mean femtosecond laser. But I guess the best is there to really get in contact with maybe afterwards via this chat with laser science, and yeah, discuss what is possible there. Yeah, is there any, right now I don't see other questions in the webinar chat. Maybe there are some other questions, or yeah, feel free to ask.
Yeah, yeah. I think there might be some email questions also coming up after this webinar. So Apeksha can send that email to you, Matthias, and then
Yeah,
we
of
can
course.
reply to the customers.
Yes,
Yeah.
I'll surely do that.
Yeah. So I said before, you're welcome. In principle, yeah, if you're in the market, to contact directly Laser Science, or also to contact us, and then yeah, in principle, Laser Science, our distributor for all our products in the Indian market. But also if it goes, let's say, beyond our portfolio, we are like happy to suggest you other thing. I mean, like yeah, other solutions if Laser Science or we can't provide you with some very specific things, like for example terahertz emitters or something like this. We don't do, or single photon detectors. This is not something in our portfolio.
Yeah, thank you, Matthias. I hope there are no more questions. If there are any, you can mail us directly at ls_marketing@laserscience.com. We'll forward that to Matthias and he'll reply to it. And I guess I would like to thank Matthias. It was really amazing presentation. Thank you so much for dedicating your time and
yeah, thank you. Thank you for the invitation, and thank you for thank you for the invitation to the webinar and to having me here. So it was really a pleasure.
Yeah, with this, we would like to wind up this webinar. Thank you all. Thank you all the attendees for participating. See you all in our next webinar. Bye, Tata.